Everyone, and welcome to the part 2 of the NVIDIA pre-meeting webinars for the Interagency Modeling and Analysis Group, Machine Learning with Multiscale Modeling Workshop webinar series. And now we have Raghav Mani, who manages developer relations at NVIDIA, and he focuses on machine learning and use cases in healthcare. And so please welcome Raghav, and he will present Rapids.
Great. Hi, folks. Today I'm going to talk about a new set of tools that we have been working on at NVIDIA called Rapids. And the goal of this set of tools is to accelerate data science workflows by using GPUs. If you were to look at the day in a life of a data scientist, the figure on the left is probably close to what most of us have to deal with. Now, as data sets have become larger, it allows us to do more interesting things with the data. But we, as a data scientist, we still have to deal with the fact that the tools are still relatively slow. So if you're building a predictive model, your typical workflow may be you pull data together and you start doing some data cleanup. But then since that takes a long time, you wait for it to happen. And then you go back and then do the next step, and then you wait again. So there's lots of starts and stops in your workflow. The goal of this new set of libraries that are collectively called Rapids is to essentially reduce those dead times in the workflow of a data scientist so that they have as close to an interactive experience as possible. I'm going to use some healthcare examples through the presentation, but you can imagine how this would relate to in other scenarios as well. So in the case of healthcare, for example, you have many different data sets that you as a data scientist might want to bring together to build a predictive model. And typically, the process of bringing those data sets together, engineering new features, and then training a model, all of these are quite time-consuming. And also, given that these are iterative processes, that you don't just do them once, but you do them repeatedly, means that every iteration is time-consuming. And since you do many iterations of them, the entire effect is that the whole workflow takes a long time. The goal of Rapids is to essentially GPU accelerate these bottlenecks so that you have that fast interactive workflow. Now, to understand how this works, let's take a trip down memory lane as to how data processing technologies have evolved over the last 10+ years. So as data sets started to get big, Hadoop was the big game in town. When you needed to do processing of data that could not fit in the memory of a single machine, and you need to scale out, Hadoop was the way to do it, which was great. At that time, that was the only tool available, but it had certain deficiencies, which is that as you process data, going from one step to the next, Hadoop you would write the data to disk from one step, and then the next step would pick it back from disk and then do some operation. And then when it's done, it would write it back again to disk. So lots and lots of reads and writes of data to disk, and which made it quite slow. So the big innovation with Spark was to move all of that data processing to the main memory. So you kept the data in memory. You never you read it from disk once, but then you kept it in memory all through the processing pipeline. And that made things significantly faster. But it still had the drawback that it was running the operations on a CPU and couldn't take advantage of the power of parallel computing that a GPU provides. So with Rapids, now you go the next step, which is you don't just load the data into memory, you load it into GPU memory, and then you do all your processing, all your operations using GPU. So it's highly parallelized and highly accelerated and completely in GPU memory, which makes it significantly faster than even what you would see with the Spark style processing. Now, even with the data into memory and GPU accelerated, you still have a secondary problem, which is that if you're using a collection of different libraries, and if the libraries don't all speak the same language in some sense, then as you pass data between those libraries, you end up having to duplicate the data, serialize the data, send it over to the other library, and then the other library will then create its own version of that same data to operate on, and then do the same thing back again before sending back something to you. So this used to be the world where if you were using a collection of different libraries, you ended up duplicating the data and spending a lot of time just converting data from one format to the other based on the libraries that you were using. And so a big change that has been happening is a move towards a standard for representing data in memory called Apache Arrow. And the big benefit there is that since all of these different libraries agree upon the standard, when they need to send data between each other, they can simply pass a pointer. Now, Rapids uses the same technology as another means of deriving acceleration, that it represents the data in Apache Arrow format, and all the libraries that are part of Rapids simply reference that one single data source. So this is how the technology stack looks like. At the bottom, you have the GPU memory, where all the data gets read in and represented in an Apache Arrow format. And then built on top of it are a bunch of different libraries that get exposed through Python bindings. So CrewDF is a data frame manipulation library. You can think of it as roughly a GPU accelerated version of Pandas. CrewML is roughly a GPU accelerated version of scikit-learn. And CrewGraph is roughly a GPU accelerated NetworkX. And there are other libraries that we're constantly building to this collection, but they all follow the same pattern. Underlying everything is the data represented in Apache Arrow in GPU memory, and then all the operations happens on a GPU, and the APIs for it are all exposed through Python bindings. Now, if the data is large enough that it can't fit in a single GPU, we can scale out. We can scale out using DAS. We can also actually scale out using Spark. So at the end of it all, you have this, you have a set of tools that are Python-based that look very familiar if you're using Pandas and scikit-learn, but now run on GPUs and can also scale out to multiple machines if you need to. So let's take a use case to see how this actually plays out. Let's take the use case of if you're trying to build a predictive model that's aiming to identify patients who are likely to miss an appointment. And this is an important use case for hospitals because resources are expensive, and if a patient doesn't show up for an appointment, that's lost revenue. And so data science and machine learning can help optimize the schedule so that if you know that a patient is likely to skip an appointment, maybe you potentially give them a reminder call and a different type of a reminder call, or maybe group them together along with other patients that are likely to miss an appointment so that the net effect is a little bit more controlled. So I'm going to play a video here that shows the process of building this predictive model, one side on a CPU-based infrastructure using Pandas and scikit-learn, and then on the right side using Rapids. And you'll see how similar the processes are and how much faster it is when you're doing it on Rapids. So I'm running the two Jupyter notebooks in parallel, and you'll have these indicators here to show progress. On the right side, the Rapids version, it has already loaded up the data. It loaded up about 5 gigabytes of data in just about 2 seconds. And this is a lot of useful patient data that are likely to be good features for this predictive model, like age and distance from clinic and weather conditions and such. Now, on the left side, you can see that the loading process is still running. It'll get done in a couple of seconds, and you'll see that it's very similar. Yeah, there you go. It's finished loading up, and you can see that it's the same kind of data that you saw on the right. And you might also notice that the APIs are quite similar between the two because Rapids deliberately follows the Pandas-style APIs. Now, the next, the Rapids, version on the right has already gone on to preparing the data and doing feature engineering. So examples of things that it's doing is, building a feature called an age bucket. So since age is a continuous feature, I want to convert that into an age bucket that is more useful for that likely will be a better performing feature than just a continuous feature. And then one-hot encoding a bunch of categorical values. I'm also building a feature that represents whether the appointment is close to a holiday weekend or not, because I think that's an informative feature. And then a train test split. And then building, and in this case, I'm training this model using XGBoost, a GPU accelerated version of XGBoost. And off we go. So you can see that the loading and the data preparation is actually already done. It took about 90 seconds. And the training is also already done. It took about 7 seconds. And obviously, we're not going to wait till the CPU version gets done because I have the numbers up above there. And it's going to take quite a bit more time for this example to finish on a CPU infrastructure. So here is a summary of what we just did. We loaded up about 5 gigabytes of data using Rapids, specifically the libraries called CUIO and CUDS. And the GPU version is about 10 times faster. But I think the more interesting one is actually the training time. The training time is about 75x faster on GPU versus a CPU. And I'm doing this on a fairly beefy CPU here, the 20-core Intel Xeon. So this is no, this is not a lightweight CPU that I'm running this on. And I'm comparing this against a single V100 GPU that has 32 gigs of RAM. Now, what does this mean? And if my training can run 75x faster, it means I can do potentially 75x more experiments. So if you're thinking about very large hyperparameter sweeps, this makes it possible to even consider it. And the net effect of all of that means that you might produce a better performing model. So that's the goal of all the speed up, is that speed up allows you to do something more, and at the end of it, hopefully produce a better model. Now here is another version of this. Now this is for an even larger data set. This is a 200 gigabyte data set. And we are comparing, in this case, we are running this on a Spark cluster and then comparing it against running it on GPUs. And so I'll focus on the training using XGBoost here. So here I'm training this on a 20-node Spark cluster, a 30-node, 50-node, and a 100-node Spark cluster. And in comparison, I'm running this on a 16 GPU box called a DGX2. Now you'll know that the interesting piece here is that as you add more and more nodes to the CPU cluster, you'll see that the performance actually doesn't scale linearly. And part of the problem is that when you have a lot of weak compute nodes, if you just keep scaling out a lot of weak compute nodes, you end up spending more time distributing the data than actually doing stuff with the data in each of those compute nodes. So this makes the case for having a fewer number of dense compute nodes, where each node does a lot of work, and you don't have to send data to a whole bunch of different nodes. And you do so only when you need to. So I want to sort of wrap things up with this. I see the evolution in these terms. Hadoop introduced the world of big data. It was scalable, but it was slow because it wrote to disk and read from disk repeatedly. Spark built on top of Hadoop and made things much faster by keeping data in memory, but its computations were still limited by the fact that they were not accelerated through GPUs. Now, Rapids takes it one step further, loads the data and keeps it in GPU memory, and then all the computations that it does are GPU accelerated. And I think this is the direction where any large data processing pipeline is going to move towards, because of the significant improvements in speedups that you get using this approach. That's all I had.